So far we have considered in detail the structure of many metallic elements and also especially the structure, the void structure, that is where the voids are present, how they are distributed and how these voids are coordinated with the parent host lattice atoms. Now we will consider the addition of alloying elements to these pure elements, and we will see some of the important structures which come about, what happens to this alloying element, etc. These alloying elements, especially in a pure metal, when you add other elements and especially when you do so intentionally, they are called alloying elements. Though in principle there is no difference between an alloying element and an impurity, but it is the intentionality which comes into picture. Even if an impurity is present, it would given the type of impurity, it will occupy perhaps the same positions as an intentional alloying element would occupy, and its role on the properties would be identical. But only thing is that when you are talking about an alloying element, it has been intentionally added to engineer some important properties in the material or to study some important aspects of phase evolution. So this might be scientific or engineering oriented goals. When the alloying element is small in quantity, often it is called doping. So doping is the term used when you add a very small amount of an alloying element, and this is typically done in semiconductors, wherein you want to produce a N type or a P type semiconductor, say for instance in silicon. Now the alloying element when you add can be accommodated in one of the three possibilities as shown here. So when you add an alloying element, it can either segregate, that means it has no solubility in the or a very little solubility in the parent lattice, and therefore it gets segregated. Suppose I am talking about a single crystal, then obviously it can get segregated only to the surface. And suppose you are talking about a polycrystal or a crystal with lot of defects, then there are other possibilities wherein this other alloying element can go. The second possibility when you add an alloying element is that it can form a solid solution. Now solid solutions are in some sense like liquid solutions, but they have certain very important differences when you contrast them with liquid solutions. When you are talking about a solid solution, there are two types, the interstitial solid solution and the substitutional solid solution. And further, both these type of solid solutions can be ordered or disordered, and of course we will take up each one of these cases in some more detail in the coming slides, but this is an overview of the possibilities. The third possibility is the possibility that the alloying element can form a compound or an intermediate structure, and this intermediate structure would have a new crystal structure. That means it would not correspond to any of the parent it would not correspond to the parent lattice, but would be a new structure, and we will see that these intermediate structures could be very different from the normal valency compounds which we often deal with in chemistry. Therefore, to summarize this slide, there are three possibilities when you add an alloying element to a material, and this alloying element could be in a large quantity or a small quantity, and I am talking about small quantity, it could be even in parts per million, in which case you would call it doping, and this alloying element could occupy one of the three positions or could go into one of the three possibilities with respect to the host lattice. Either it could segregate or phase separate, that means that it has got very low solubility in the parent lattice. The alloying element added could form a solid solution, and these solid solutions could be interstitial type or substitutional type, and as we shall see that this solid solution could be ordered or disordered, and finally it could form a compound or an intermediate structure. So let us take up the first case, which is segregation or phase separation. And when I am talking about segregation, I mean that the alloying element has low solubility, and whenever I add more than the solubility limit, then the extra material added would obviously segregate. And we should note that whenever I am talking about negligible solubility or zero solubility, what I exactly mean is that it is limited to very small amount. Zero solubility theoretically is not possible, because we know that because there will be a reduction in Gibbs free energy due to entropic benefit, and therefore some small amount of the alloying element would always dissolve in a parent lattice. Okay. So this is coming purely from the benefit in Gibbs free energy if you are working at constant temperature and pressure, and that is the benefit to the Gibbs free energy is coming from the multiple configurations which are possible when you add an alloying element. Therefore, some little solubility is always guaranteed, but in this case what we are talking about is a larger quantity of solubility, that means a larger amount of the alloying element is trying to be put into the matrix, and if that solubility is very limited, then it may segregate. Of course, this segregation can be called a separate phase, and when I mean a separate phase, suppose I have two elements A and B, then the two insoluble phases in each other would be that the phase A would have a little amount of B and the phase B would have a little amount of A. And typically when you talk in a language, you will call them the terminal solid solutions, and you will call them by alphabets alpha and beta. Okay, so there is some little solid solubility which is always guaranteed, and you would call them the terminal solid solutions alpha and beta.
Sir, what is the difference between solid solution and liquid solution? Actually, such as LCP, this is a liquid solution, and also is called a crystal, liquid crystal. But solid solution, it is alloy or something different?
Okay, good question. When I am talking about a solid solution, definitely it is an alloy. Yeah. So especially I could give an example. You could add copper to zinc, or you could add manganese to aluminum, and there are so many other possibilities. So these are all examples of alloys, and we will take up some more examples in the coming slides. In a liquid solution, as you can note, that there is no specific lattice of the host, there is no specific position into which a solvent atom would go into. But in the case of these crystalline solutions, we note that there is a parent lattice, and therefore with respect to that lattice, my whole solubility or the solid solution has to be discussed. And as I mentioned that you could have interstitial solid solutions, in which case the added atom would go into the interstices, or it could be replacing a parent atom. And there are very specific cases wherein an atom would go into either the interstice or the host position. So there are those kind of possibilities also, which are very rare.
So how we call solutions? These are some solid alloy.
Yeah, precisely. They are called solutions because it is a hangover of the terminology from liquid solutions, but essentially what you are telling is true, that they are an alloy. Okay. Okay. So as I said, if you are not talking about a single crystal wherein the segregation can occur only at the surface, then if you are talking about either a polycrystal or you are talking about a material with lot of defects, we have not yet considered some of these defects, and therefore we will take these things up later during our course, but it is just worthwhile to note at this point of time. Suppose I did not have a single crystal but a polycrystal, and let me draw a crude schematic of the polycrystal on the board for you to understand. For instance, now as you know, any real material has to be finite, and therefore it cannot be infinite extent in space. So this is my single crystal, and suppose this is a particular planes in my single crystal, which are, for instance, if I consider an FCC crystal, for instance, this could be the 100 planes. Okay. Now if this single crystal, then this is all the crystal I need to consider, but suppose I am talking about a polycrystal and any common metal, for instance a copper wire or a piece of aluminum which is used in structure, are all polycrystals. In fact, single crystals are much rarer to find. Then you would notice that there will be other regions around it, other crystals. For instance, this is of course a crude schematic which have different orientation of these 1-on-1 planes. Of course, this is a 2-dimensional picture. In 3 dimensions, this could be the 100 planes, and alternately I could even draw, for instance, the 100 direction in some of these, and I can show that say in one of these other ones the 100 plane could actually be coming out, or the direction coming out, and again some inclination. In other words, each one of these crystals is oriented differently with respect to its neighbors. Okay. And therefore the alloying element I add, if it is not soluble within the crystal, can either go to the free surface, assuming this is now my free surface, so it can go into this free surface, or it could get into the grain boundary region. So it could actually get, let me use a different color chalk. Grain boundaries are typically regions of higher free volume, and so therefore it could get into these grain boundary regions. And therefore the alloying element could go and sit here. Obviously the amount of grain boundary region per unit volume of the material would be a function of the grain size. You go to smaller grain sizes, you would find that means grain size being the size of this crystallite. Smaller the grain size you go, you will get larger amount of grain boundary area per unit volume, but you have to remember this is still a limited amount of volume available for a volume of the sample. Therefore the amount of material which can go into for instance this grain boundaries is very limited as compared to the total volume of material available. So even in this case, the segregation to the grain boundary would mean a small amount of material as compared to the total volume of sample available. Again further there could be even lower dimensional effects. For instance, there are line defects known as dislocations, and the material you added, for instance I can give an example, for instance carbon in BCC iron can go to these dislocations and sit there, typically the dislocation cores, but again the amount of dislocation core available would be a function of the dislocation density, but again is small compared to the total volume of the material. But these are possibilities. In other words, when I add a alloying element and it has exceeded its saturation limit, solubility limit, then it will go and sit in one of these other places, and this has profound consequences in terms of the properties of the material. For instance, when carbon sits in BCC iron, you will find an effect known as the yield drop when you do a stress strain diagram. When certain materials, for instance, go and sit in the grain boundary, they can severely affect the properties of the material. To give an extreme example, for instance, when you add gallium in aluminium, it can actually go and sit on the grain boundary, and often the gallium diffuses through the grain boundary very fast and actually can lead to severe weakening of the crystal, and often this crystal would just separate under tension. So in other words, when I am adding an alloying element, the alloying element itself is going to give me some effect when it is within the host crystal, but additionally when it tries to segregate to some of these other defects in the material, it could cause very different kind of effects in terms of the material behavior. Now when I am talking about a solid solution, and especially a solid substitutional solid solution, then the solubility is governed by a set of rules. Of course, these are guidance rules, and they are not what you might call strict theorems. They are more like guidance rules, and these are known by the name of the Hume-Rothery rules, which we will take up next when you are talking about solid solubility. The second possibility is, which you have been of course discussing already, is the possibility of the formation of a solid solution. In this case, I am assuming that I am within the solubility limit, and often this solubility limit could be pretty large. The extreme case would be when I am talking about an element A and B, and any proportion of A is soluble in any proportion of B. In the liquid analog, you can talk about, for instance, alcohol and water mixture. Alcohol dissolves in water in any proportion. Similarly, you could have a solid solution case, and wherein you can add any amount of A into B, and this kind of possibility only exists in substitutional solid solutions, and in the case of interstitial solid solutions, typically you do not find complete solid solubility. And this we had already discussed when we were talking about the voids in some of these simple crystal structures. We had noticed that when you add a parent or a alloying element which goes into the void, then it causes a distortion to the lattice, and therefore it causes energy to the system, and hence when you cannot add too much of this alloying element to the interstitial positions. And we will also see that when you are talking about ordered systems, you can even have interstitial solid solution which can get ordered. Now to emphasize the point which Patel made, the mixing is at the atomic scale and is analogous to a liquid solution. Now in the context of these solid solutions, it is worthwhile to note that when you have pure components, we typically denote them by alphabets like capital A, B, C. When you have solid solutions, we denote them by alpha, beta and gamma. Typically, for instance, alpha and beta are used for terminal solid solutions, that means solid solutions which are close to the pure compositions A and B. And you could have ordered solid solutions as we mentioned before, and you use a prime. This prime is used to designate that we are talking about an ordered solid solution. So suppose I had a disordered solid solution, I will call it alpha, and the ordered version of that would be called alpha prime. Just to summarize this slide once more, when I add a parent to the parent lattice or to the parent crystal, when I add an alloying element, depending on typically on the size of the alloying element, either it can replace or go and sit in a lattice position, or of course when I say lattice position, I mean that any one of the lattice or motif positions, any positions available part wherein the large sized atoms sit, or it could go into one of the interstitial positions. Okay. And further, these solid solutions can be disordered or ordered. Now I talked about the Hume-Rothery rules, which govern the rules which tell you that when would I get extensive solid solubility in the case of substitution solid solution. And these are empirical rules which govern the formation of substitution solid solutions. These are simple rules to understand, and they can be rationalized in terms of our usual common sense materials thinking. The first one is that the solute and solvent atoms do not differ by in other words large size. The difference in diameter is typically less than 15%. Smaller the size difference, larger we expect the solubility to be. This is obvious because when you put a atom into a parent lattice which is very large, very different in size as compared to the host atom, then the distortion cost to the lattice would be large. The second rule says the electronegativity difference between the elements is small. This is again easy to understand. If there is an electronegativity difference which is very large, then there would be a tendency to form compounds and not form solid solutions. Again, the valency and crystal structure of the elements is same. So, the closer the valency and the crystal structure, the closer would be the solid solubility. Now, this is again easy to understand. What these rules are in other words saying is that like dissolves like. So, if you have elements which are very similar in size, in valency, in crystal structure, then the solid solubility would be extensive. Now, suppose let me take another extreme. If the crystal structures are very different, for instance, one is an FCC, other is an HCP, or one is a BCC and other is say a tetragonal crystal. Obviously, a complete solid solubility of A in B is not possible, because one hand you have a say a face-centered cubic crystal, other hand you have an hexagonal closed packed crystal. So, somewhere you can notice that the transition has to take place, and that means that complete solid solubility of A in B or B in A is not possible in that case. There is an additional rule which is cited along with the Hume-Rothery rules, which says that an element with higher valency is dissolved more in an element of lower valency rather than vice versa. So, we will take up an example to actually illustrate this principle, that how an element with higher valency is dissolved more in an element of lower valency than the other way about. So, we will take up an example to understand this. So, let us look at the applicability of the Hume-Rothery rules and also the exceptions with regard to some specific examples. The first example here is these three examples here in this table are examples wherein you find complete solid solution in all proportions. That means I could take element A in 40% or 20% or 5% or 95% and add element B, which is of course the specific element here in this table, and I would get complete solid solubility. That means I would obtain a solid solution. These examples are silver, gold, copper, nickel, germanium, silicon, and you can see that the first two relate to an FCC solid solution. Germanium, silicon are both diamond cubic crystal structures. Now, let me take the first example, silver and gold, both have the same crystal structure, both have the radius of the atoms is very similar, to second decimal place they look very similar, the valency is very similar, and the electronegativity difference is also not too large. So, I obtain complete solid solubility between silver and gold, and you know that silver and gold are noblish metals wherein you would expect complete solid solubility. Now, the second example is between copper and nickel, and if I look at the crystal structures, again the crystal structures are both FCC. The size difference, the radius of the atoms is almost similar. In fact, it is only different in the second decimal place. This is 1.28 angstrom, this is 1.25 angstroms. The valency is different, but again not too much, and the electronegativity difference is also not too much. So, this is a second example wherein you find complete solid solubility between copper and nickel. The third example is of course an interesting example because it happens to be diamond cubic crystal, and in the diamond cubic crystal structure, of course, you have atoms located at 0, 0, 0 and quarter, and suppose I take a germanium crystal and start adding silicon, it would go and replace any one of the atoms in any of these position and would continue to be tetrahedrally bonded to the other atoms in the crystal structure. If you look at the radius, they are very similar. Of course, even this difference, for instance, would mean that there will be some strain, but the strain would be small. The valency is identical and the electronegativity difference is also negligible. Therefore, you can see that these are nice examples wherein you get complete solid solubility, wherein the elements obey our Hume-Rothery rules. Okay. Now, the exception to this also exists. In other words, when you find that some of these parameters are satisfied, even then you may not get complete solid solubility. And the example usually cited is the copper gamma ion example, wherein some of these criteria are satisfied and still you never find complete solid solubility. So, as I again point out, just to emphasize the important thing, these are guiding principles. Hume-Rothery rules are guiding principles, and it is not a strict rule in the sense that if these rules are satisfied, then you would get complete solid solubility, and the example here to disprove that it is actually not a theorem is the fact that there is the example of the copper gamma ion, wherein you do not find complete solid solubility. Now, I had mentioned when I had talked about the Hume-Rothery rules that an element with higher valency is dissolved more in an element of lower valency than rather than vice versa. So, just to illustrate this with an example, I have got an example here, and this is the example of copper and zinc. So, you can straight away see that there is no reason to expect complete solid solubility in this case, because copper is FCC and zinc is HCP. So, there is no possibility for us to obtain complete solid solubility. Now, if you want to contrast it with liquids, then this crystal structure aspect is obviously absent, and therefore, some of the guiding principles would be very different. Now, when I am talking about solubility, if you see that copper has a valency 1 here and zinc has a valency 2. So, the higher valency element is zinc, and as the rule says, the higher valency element dissolves more in the lower valency element, and the solubility in this case happens to be 35%. That means, I can dissolve 35% zinc in copper, while if you look at the other part of the diagram, that how much of copper can I dissolve in zinc. So, copper is the lower valency element and zinc is the higher valency element, and therefore, you can see the solubility is very limited, it is only 1%. So, just to reiterate the principle and summarize this diagram, so that you have a better understanding of this rule, it says that, so let me, since I have got the slide in front of me, let me revise the Hume-Rothery rules for you and these empirical rules. The solute and solvent atoms do not difference in size by more than 15%. That means, they should have as similar a size as possible. The electronegativity difference between the elements is small. The valency and crystal structure of the elements is as similar as possible. An additional rule, which is what I was explaining now, is that the element of higher valency is dissolved more in an element of lower valency rather than vice versa. And the example I am citing now is the example of copper and zinc, and as I pointed out, because the crystal structures are different, there is no reason to expect complete solid solubility, but then when I am trying to track the asymmetry in the solubilities, that how much, suppose I call this A for instance and I call this B, then I am asking the question how much of B would go into A and how much of A would go into B. I can clearly see that this asymmetry is pronounced, it is not just a slight asymmetry. That means asymmetry with respect to the 50-50% composition. The element with higher valency zinc dissolves much more in copper, and that is 35%, and the element with lower valency, which is copper, dissolves very little in zinc. And of course, these solid solutions, if I am talking about the solid solutions which lie in this region, let me take up a different pointer for instance. So, I am talking about solid solutions in this region, then obviously all these solid solutions would have a FCC structure. That means, I will have a parent host crystal made up of copper atoms, wherein I will slowly, as I increase my percentage of zinc, I will keep on replacing more and more of copper atoms with zinc atoms. On the other hand, these solid solutions, so for instance, using my normal terminology, I could call these solid solutions of alpha and these solid solutions as beta, and when I am using alpha and beta, I mean they are disordered solid solutions. So, in this region for instance, wherein I am finding beta, obviously you will have an HCP crystal, wherein in the zinc crystal structure I would slowly replace some of the atoms with copper. Okay. So, this is my copper zinc system. We will also later on discuss some other interesting crystal structures from this very same copper zinc system. Okay. Now, I had mentioned that when I am talking about an interstitial solid solution or a substitution solid solution, I can have two possibilities, the ordered and the disordered structures. When I am talking, already we have dealt with this concept in previous lectures, that what is a disordered structure, what is an ordered structure, and we had clearly seen disordered structures are described by the language of probabilistic occupation. That means that suppose I have 50 alloy, 50% of A and 50% of B, then I would say that any lattice point there is a possibility, suppose I am talking about a simple BCC crystal, then I have 50% chance that A occupies any lattice point or 50% chance that B occupies any lattice point. On the other hand, when we talked about ordered structures, we we used a language of subcrystals and sublattices, right? We had used that language. So, we need to understand that when I am talking about ordered structures, I need to use a language of subcrystals and sublattices. And it is important for us to understand this ordered disordered transformations and typically pick up some examples of these ordered structures. Now, it is typically found that the high temperature phase is the disordered phase, while the low temperature phase is ordered. Wherever you do observe ordered disordered transformations, you will see that the high temperature phase is the disordered one and the low temperature phase is the ordered one, and we will rationalize it in terms of the Gibbs free energy in one of the coming slides. We already noticed that when we are talking about order, I could be talking about two kinds of order, orientational order and positional order. Though most of the examples we will be taking up in this lectures would be related to positional order, but I will give you one example or perhaps more than one example of orientational order as well. Nevertheless, again whenever you are talking about a disordered phase orientationally or positionally, it will be the high temperature phase and the low temperature phase would be the ordered phase. In the case of positionally ordered structures, we have already seen that the ordered structure can be called a superlattice, and the superlattice can consist of more than one interpenetrating sublattices, and typically each one of these sublattices is occupied by a specific element. So, we have already seen that you could have one sublattice, two sublattices or more sublattices, and we also noticed when we took up an example on the board that we could actually have two sublattices, one completely ordered with respect to an element say A. The other sublattice could be actually occupied by two different elements B and C, and there could be that sublattice could be disordered with respect to B and C. Okay. So, therefore, there are only two sublattices. Sublattice A is purely occupied by A. The second sublattice, sublattice 2, is now occupied by B or C, and it is occupied by B or C in a random fashion. And now the stoichiometry will tell me that how much of each lattice point in the sublattice 2 is occupied by B or C, and that would depend on the percentage of B and C in the alloy. So, these are the possibilities. So, let me take up some examples also to understand this ordered disordered transformation. The simplest and the nicest example perhaps is the example of the copper-zinc system, wherein you have 50% copper and 50% zinc. And as I had mentioned, the high temperature phase is the disordered one and the low temperature phase is the ordered one. And now, we will of course emphasize this later again once more. We have to note that the properties of the system change when you have an ordered disordered transformation. That means that the ordered phase and the disordered phase are not the same phases. In fact, they have different crystal structures and all the properties would change, and that is why we need to be careful whenever we are talking about, I can't just work in terms of compositions, I have to work in terms of the exact crystal structure. In other words, I need to know, am I working at the high temperature phase or I am talking about the low temperature phase even for a given composition. So, some of these concepts we already covered in detail, so it is not difficult for us to understand them. So, the high temperature phase, for instance, in a 50% copper 50% zinc alloy is a BCC crystal structure. In other words, it is a BCC lattice wherein the motif is a 50% probability of copper or 50% probability of zinc occupation at each lattice point. Now, this is the BCC phase, that means that the fundamental lattice translation vector now is the one which connects atom at 0, 0, 0 to the atom. So, these are identical, because now these are identical not in reality, because in reality this, if you take any region of space, this could end up being copper and this could end up being zinc and this could end up being copper. So, it is a random occupation, but this is now a probabilistic sense of definition. So, that we have already noted, because in the very strictest sense this structure cannot even be called a crystal, we already seen. So, this is a crystal only in the probabilistic sense, that we have already noted, and given that important point, we already noted that this is actually a BCC crystal with the fundamental lattice translation vector, or the shortest lattice translation vector being half half half, whose length is √3/2a. See, all these aspects we already seen. Now, what about the low temperature ordered phase? The low temperature ordered phase can be now described as two interpenetrating simple cubic lattices or simple cubic crystals. Origin of one lattice at Z0, 0, 0, the origin of the other is at half half half, and the important point now to note, this is not a BCC crystal, we already know this. This is a simple cubic crystal, and this simple cubic crystal has a motif which is one copper atom here and one zinc atom here. Of course, I could always place the origin at half, in which case the motif would just flip its positions, but nevertheless this is a simple cubic structure. So, when I go from a BCC high temperature phase to a low temperature simple cubic phase, which is now an ordered structure, the properties of the whole material will change along with it. Now, for instance, now the shortest lattice translation vector would be this, which joins the 0 0 0 to 1 0 0. It is no longer the vector of the form. For instance, in this case the shortest lattice translation vector was half 1 1 1 vector, and in this case it will be the 1 0 0 vector. Therefore, this ordering transition is also accompanied by change in properties. For instance, if I want to describe the slip systems in these two crystals, they will be different, and the Pearl stress, for instance, the fundamental stress I need to apply to drive plastic deformation in these materials, that would change, and therefore many other properties would change along with this change in crystal structure. Now, the question we are asking is that why is the high temperature phase the disordered phase and the low temperature phase the ordered one? The answer lies in our Gibbs free energy. Okay. So, we notice that the temperature is the weighing factor for entropy. That means, at the higher temperatures the structure with higher entropy is stabilized, and lower temperature the structure with lower entropy is stabilized. Now, suppose I had two sublattices, of course assuming that it is a completely ordered system, then one sublattice would be occupied by one element, the other sublattice by the other element, copper and zinc in this case, and therefore the number of configurations available to me is none. There is just one possible configuration. But suppose I am talking about a disordered phase, then I have many configurations which can finally give me a 50-50 probability at each lattice point, and therefore the system becomes configurationally rich, and according to Boltzmann equation S equal to k ln omega, I would notice that disordered structure is preferred at high temperature. So, this is purely coming from the Gibbs free energy arguments. So, just to summarize this slide and also the concept of positional order, that I can describe my disordered crystal at high temperatures using a probabilistic occupation model. The low temperature phase, typically which is the ordered phase, which for instance I told you, suppose I call this by symbol gamma, then I will call this gamma prime, because now this is an ordered phase, the lower temperature phase, then there is a substantial change in properties. Now, for instance, this transformation in this particular system occurs at 470 degrees for a composition of 50% copper and 50% zinc, and I can understand this disorder transformation in terms of the Gibbs free energy driven transformation. Now, I have listed here some of the salient features about ordering, and this is an extensive list, and I will go through this slowly one by one, so that we can understand some of the important aspects of this ordering phenomena. Ordering takes place because the AB bonds are preferred compared to the AA or BB bonds. In other words, when I have a structure like this, you can clearly see the environment of the copper atoms is completely zinc. So, it has got an 8-fold coordination of zinc around the copper atoms. In this case, of course, the environment is random. So, there is no specific coordination out there, and therefore, whenever an atom of a different atom prefers different types of neighbors, that means the AB bonds, that means the copper zinc bonds are more energetically favorable as compared to the AA or BB bonds, then you find the phenomenon of ordering. The important point to note is that the ordered alloy, and in the previous example I would call the copper-zinc alloy, is an example of something known as the intermediate structure, and this would form in the case of limited solid solubility also systems also. The structure of the ordered alloy is different from both the component elements. For instance, in the previous example, copper FCC is equals HCP, but the ordered alloy was in simple cubic, had a simple cubic crystal structure. So, we have to note this, that the ordered alloy is different from both the parents, and this is an important point to be noted. Arun has some questions.
First question is what factors govern segregation?
Okay. So, we already yes, what is the second question?
Second question is can we say that substitutional solid solution is always followed by vacancy, or because in you say that the alloying element will sit on the void, some vacancy or some vacancy, sorry. Is if there is some vacancy, it will sit there, or is it followed by vacancy or some what?
Okay. Perhaps two good questions. Let me answer the first one first. When I say, so let me consider substitutional solid solution. If I am talking about an element which is soluble, that means I am following my Hume-Rothery rules, and of course we have already seen that Hume-Rotheries have their own limitations, but assuming that Hume-Rothery rules are cardinal for my explanation of solid solution, whenever I do not have those criteria being met, then the second element cannot dissolve in the parent lattice, say in the wherever the lattice, it has to replace an atom in the lattice point, therefore it will segregate. Now the question we are asking, of course, is that where would it segregate? Of course, you have only, it is a single crystal, the only place it can segregate is to the surface. Okay. In a polycrystal and in a defected material, there are other possibilities where such a second, where the alloying element or the dopant or the impurity, whichever way you want to call that added element, can segregate. So these are the other possibilities we have noted, and I said that little detail matters a lot to me regarding my material properties. As I said, if gallium segregates to the grain boundary because it cannot dissolve in parent aluminium, host atom, it can't replace its host atom aluminium, then the material becomes extremely weakened. There are other phenomena which are similarly found in steel, wherein the alloying element not only segregates to the grain boundary region but also could form a compound. Okay. Now the second question is related to the vacancies. Now let us be very clear. The vacancies, again, of course we will see that vacancies can be more than one type. So you raised an important question of what is a vacancy. First of all, we will answer this, what is a vacancy, what kind of vacancies exist in crystals, in an upcoming lecture. Just for, since you asked me this question, a vacancy for the sake of audience is, for instance, if you take an FCC aluminium, then it's an atom missing from the lattice point. So suppose I do not have an aluminium atom, an ion, and it is not present in the lattice point, I call that a vacancy. Now my solid solubility is, in principle, of course, in the simplest sense, is not dependent on the vacancy concentration, because what I am saying is that when I am adding, for instance, in this case I am adding copper to zinc, then the copper is replacing zinc in its lattice position. Okay. So it is not that, of course, then that means replacing means I do not take away the zinc, I mean that I am filling larger volume, I am adding more unit cells, wherein I can selectively in some of the unit cells I will put copper instead of the zinc originally present. So there are no vacancies here. Of course, if I am asking more specific questions of what will happen to the diffusion of these alloying elements, which we will perhaps consider later, then vacancies play an important role. Yes, if there are pre-existing vacancies, for instance in the zinc crystal, then copper can obviously go and occupy those vacancies as well. That is a possibility.
How we define solubility? Because normally we say that at high temperature solubility is more, at low temperature solubility is less. So for segregation we said that we should have low solubility, very low solubility. So is there any temperature boundation on that? Because in case of solid solutions we are saying that high temperature disordered, low temperature ordered case. Or is there any possibility that high temperature because the solubility is more, it forms some solid solution, or low temperature it forms it leads to segregation?
Okay. Now the question you asked is slightly more difficult to answer at this stage, because we have not really considered the concept of phase diagram, the concept of solubility, the concept of solubility, competing phases. Let me give an example, even though this is slightly advanced for this stage. That suppose I am talking about solubility of carbon, which is an interstitial solid solution, and we will be taking that up in this lecture, a carbon in BCCN. Now obviously this carbon goes and sits in the interstitial position, and we have already seen it sits actually in the octahedral void position. Okay. Now the solubility of carbon in alpha ion, which is the ion BCC form of ion with carbon in it, keeps on increasing to a certain temperature, which we call the eutectoid temperature, but after that actually decreases, because now the alpha phase originally is in coexistence with the Fe3C, which is cementite, but later on after the eutectoid temperature actually it is in coexistence with the gamma phase. So actually the solubility decreases with temperature. So it is not a general rule that solubility always has to increase in the alpha ion with temperature. That is point number one. But as a general rule, yes, because you have this Gibbs free energy benefit, therefore with increasing temperature you would find a larger solubility. So that possibility exists. So what is your specific question?
Because in substitutional solid solutions we are saying that high temperature disordered phase and low temperature ordered phase, but can there be any possibility that high temperature solid solution forms because of high solubility, and low temperature it results in segregation?
Absolutely, absolutely. That possibility always exists. And in fact, in fact, segregation is the opposite of ordering. Segregation is where A type of atoms want to have A type of atoms around it. Ordering is A type of atoms want to have B type of atom around it. So segregation is the opposite of ordering. In other words, in some sense, segregation is clustering. And either the system will show ordering or they will show clustering. So both these possibilities exist, though not the same system and the same composition. That you have to note. Some systems would show ordering, some systems might show segregation. So that we have to note, yes, that is absolutely a possibility. So getting back to this list on ordering, now we have noted that the structure of the ordered alloy is different from both the component elements. So that is an important point to be noted. The formation of the ordered structure is accompanied by change in properties. So this point I had already mentioned, and the example would be, for instance, in permalloy, ordering leads to the reduction in magnetic permeability and increase in hardness, etc. In other words, the ordered structure, the disordered structure can be thought of as a solid solution, while the ordered structure is something similar to a compound. It is something similar to an intermediate phase, and therefore this intermediate phase, which has a different crystal structure, has different properties, and this point has to be clearly understood. And when you consider more examples, all the more it will become clear that why the properties would change, because the crystal structure is changing. And I am talking about ordered solid solutions, and of course when I mean complete here, I mean complete ordered solid solutions are formed when the ratios of components or ratios of whole numbers like 1:1, 1:2, 1:3, etc. And in the examples here, for instance, copper to gold ratios 1:1, CuAu the ratio is 3:1. When you find these whole number ratios, then the possibility of forming ordered solid solution is complete ordered solid solution is there, and it will become clear from the for instance, even from the previous example it will be clear. Now suppose I have a ratio of copper to zinc here 1:1, then a complete ordering is possible. If I have more than 50% copper, say for instance I have 51% copper, then this system can never get totally ordered, because 1% of the copper has to either go and sit in the zinc positions, or I will have to leave some of the zinc positions vacant so as to maintain my stoichiometry, right. In other words, in a off stoichiometric, suppose I take a copper and zinc off stoichiometry, and this is just an example. The more general example would be A, B. If I consider an off stoichiometric composition, then such a thing cannot never be obviously completely ordered with respect to that structure. And just to emphasize, the ordered solid solutions are in some sense between solid solutions and chemical compounds. When I mean chemical compounds, I am referring to what we normally call the valency compounds, or the standard chemical compounds we deal with in chemistry like H2O or one of those compounds. So this is important to be kept in mind, that these ordered solid solutions are neither in full sense chemical compounds, in which case of course my stoichiometry will be completely fixed and I cannot change my stoichiometry. They are also not random solid solutions, and they are something in between, and this is an important thing to be noted. The degree of order decreases on heating and vanishes on reaching a disordering temperature, and in this sense it is not like a compound. In other words, and of course I will tell a little more about what I mean by order and degree of order, how do we define degree of order, and what I mean by this word order also, and I will tell a little more. But the important point to note is that this disordering does not take place at a single temperature usually. Of course there are special cases, and this degree of order slowly decreases, and in this sense most of the order disorder transformations are second order transformations, and it vanishes, that order completely vanishes with an increase in temperature, and therefore this behavior of it is not like a normal compound. And this is what I was mentioning before. Just to emphasize this point once more, off stoichiometry in ordered structure can be accommodated in more than one way, for instance, and this is something very important to note. And the very fact that I have an off stoichiometry in an ordered structure tells me that that structure will never get completely ordered, because as we can see, if I am talking about a simple example would be nickel aluminum, where I have 50% nickel and 50% aluminum. This is my composition, and this forms with a B2 structure, and when I say a B2 structure, I mean this kind of a structure, this ordered structure, which is a simple cubic structure. Now the aluminum rich compositions, that means that if I have nickel less than 50% and aluminum more than 50%, for instance I could talk about 49 Al51, then the aluminum rich composition result from vacant nickel sites. So, if because I am removing nickel from nickel sublattice or the subcrystal, automatically it becomes aluminum rich. But the important thing to be noted here is the asymmetry between going to aluminum rich side and to the going to the nickel rich side. When I go to nickel rich compositions on the other hand, that means for instance I could take a nickel 51 aluminum 49, then this result from anti-side defects. In other words, now since I have more nickel, this nickel starts sitting in my aluminum sublattice. That means the aluminum sublattice cannot get fully ordered. What is a fully ordered aluminum sublattice? Wherein all the aluminum sublattice is fully occupied by aluminum. But now because of the composition variation, and this composition variation tells me that this is not like an standard chemical compound, wherein you cannot tolerate such kind of H2O means precisely 2 hydrogen molecules for every, or 2 hydrogen atoms for every oxygen atom. But here I can tolerate this of stoichiometry, and nickel rich composition forms when nickel starts sitting in aluminum sublattice. So, you can clearly see first number 1 is the fact that there is a pronounced asymmetry in the way my of stoichiometry is accommodated, and this for instance is one nice example when in nickel aluminum system, wherein the aluminum rich compositions are occupied are accommodated by putting, that means removing nickel atoms from their nickel sublattice. So, already we have seen a lot of important things related to ordering, the fact that it's you can call an ordered structure as an intermediate structure. It forms when the AB bonds are preferred, that means bonds of a different kind are preferred compared to the bonds of the same kind, and to which was nicely answering some of the questions raised by Arun, wherein we saw that if atoms of bonds of the same type are preferred, you would have clustering or segregation. And the important thing which we finally saw is that how this of stoichiometry is accommodated in ordered structures. Now, this is just to emphasize some the point which we have been talking about, that the high temperature structure is disordered because of the entropic aspect which comes into play, and the low temperature structure is the ordered structure. Okay. And as Arun pointed out, there are other possibilities wherein you may not get ordering, but actually you may get segregation. And so, in this case there is a negative enthalpy of mixing. I was talking about disorder, and one of the important things we need is to actually quantify disorder. Okay. Because I told that this is not a 1-0 situation, that means it is not like above a certain temperature it is completely ordered and below a certain temperature it is completely disordered, or below it is completely ordered and above completely disordered. This happens over a range of temperatures. In other words, in a specific alloy I could have, and especially as we have seen in the case of stoichiometry alloys, I could have a certain amount of disorder built into the system. Now, how do I quantify disorder? Typically this is quantified by something which is called L. This L is called long range order, that which also gives me a clue that there is something else which I can call short range order. And in fact, we had considered this aspect when we talked about crystals, that crystals some cases can have long range order, they have short range order, and you could have situations wherein you have short range order missing but there is long range order, and the converse is also possible wherein there is short range order present but there is no long range order. So, this L is the long range order parameter, and it is defined as Ra minus Xa divided by 1 minus Xa, wherein Ra is the probability that the A sublattice is occupied by the right atom, and Xa is the mole fraction of A in the alloy. So, this long range order is defined with respect to A, and equivalently you can describe it with respect to B. So, let me take an example. For instance, suppose I have an alloy wherein Ra is the probability that A sublattice is occupied by the A atom. Say 90% of A atoms are actually rightly sitting in the A sublattice, that means 10% of sitting in the wrong sublattice. So, and my mole fraction is 50-50, that means I am talking about AB alloy, A50 B50 alloy. So, I can write this equation as, so I have 90% of my A atom sitting in the right sublattice. So, my Ra is 0.9, my composition is A50 B50. So, L is Ra minus Xa, 1 minus Xa, and my composition is A50 B50, that means Xa is 0.5 and 1 minus 0.5. So, this is 0.4 by 0.5, which is 80%. So, or 0 point or 80%, that is better. So, this means this long range order parameter is 80% or 0.8. Okay. And as a disordering is complete, you will find that each atom is randomly present. That means that Ra will approach 0.5, Xa will be 0.5. So, 0.5 minus 0.5 will be 0. That means the order L will become 0. Okay. So, this is my long range order parameter, and as I pointed out that there is another way of looking at order, which is looking at the short range order. Okay. And this is important for us, and let me take two examples here, though we are not considered the crystal structures of these two. One is CuAu, another is CuZn. Of course, the CuZn is this one. We already considered the CuZn example, which is nothing but a B2 structure, which is a simple cubic structure, but we are not considered the Cu3Au, which we will take up in the upcoming slide. But what I am focusing here is the change in order with temperature. And now I am not only talking about the long range order, but I am also talking about the short range order. Okay. And now suppose I have perfect ordering, that means that all my Ra atoms are sitting in the right place, which means that this is 1, 1 minus 0.5 is 0.5, 1 minus 0.5 is 0.5, that means L is equal to 1. So, perfect order would be given by long range order parameter 1, complete disorder would be, that means the complete random occupation of A and B in both the sublattices, that means there are no sublattices, would be characterized by a long range order parameter 0. Therefore, my order parameter changes from 1 to 0. This is the extent of my long range order parameter L. So, I can plot my L with respect to temperature. I can see, first let me track the long range order parameter, which is shown in red. The short range order parameter is shown in, that means the existence of short range order is shown in green. Now, you can see that the order slowly decreases, and after a certain temperature, now this is given by Tc, there is no order. But the important point to note is that even though when I am talking about no long range order, still some short range order might persist. This is the important message and the only message I want to give from this graph, because this involves some concepts which are not covered so far. Therefore, I will not go into the details like what I am talking about as a first order or a second order phase transformation, but what I want to point out here is the fact that whenever, even though the long range order has vanished, the short range order persists. Okay, this is an important thing to be noted from this, and this can be seen for both the Cu3Au type and the CuZn type ordered structures, which are different ordered structures, and you can see even here after the long range order has vanished, the short range order persists. So, this is something important to note. So, let me consider these two alloys. For instance, now I have talked about the CuZn, I have Cu3Au, and for instance, this is described here. These two, what are these crystal structures? How is this ordering different from the ordering we saw in the copper, instead of the copper-zinc system? So, this also brings us to some more interesting class of alloys, some in other intermetallic alloys which are ordered. And we already considered the FCC crystal in detail before, right, which is the structure of copper, aluminum, etc. And we have seen that there is an FCC lattice which is now occupied by the single element. But now these are more complicated structures, and there are two elements now, therefore this is an alloy, and therefore we have now gone to the next level in terms of the understanding of crystal structures. So, let me try to understand the crystal structure of the CuAu, which is now an ordered intermetallic alloy. So, when I am saying ordered intermetallic alloy, I mean that there are specific sublattices for instance the gold and the copper in this case. Now, so this structure clearly is not a cubic structure, as you can see, because it does not have four three-fold axis. In fact, it has just one four-fold axis, which is the axis going upward. So, this is my tetragonal structure. So, this is my tetragonal structure, and as you can see that this structure can be understood by replacing all my face centering positions in the mid plane by copper atoms. So, I have copper atoms or ions sitting in the mid plane, while these planes are occupied by completely gold ions or atoms. So, I have this structure can be understood as alternate planes of copper and gold, which pervades the structure, and now the symmetry of the structure has been lowered, right. So, now this structure is not a cubic structure, but is actually a tetragonal structure. So, and there is a notation known as the Structure-Berish notation, wherein certain alloys are named by certain alphabets and numbers, and this is called an L10 structure in the Structure-Berish notation. There are analogous structures like titanium aluminum, which also have the same kind of structure, which is also an ordered alloy. And so you can see that this structure can be, I will just view this structure in more than one way so that I can understand. So this is my standard ball and stick model, this is my space filling model, wherein I can clearly see that the gold occupies these face centering positions, and in these layers, and in the middle layer all the face centering positions are occupied by copper. As the lattice parameters of copper and gold cannot be identical, therefore this alloy would also have a lattice parameter C, which is different from A. So this is my C axis and this is my A, for instance, and therefore I can see that my A lattice parameter is 3.6796 and my C is 3.67. So I would use this kind of a tetragonal unit cell to describe this kind of a structure. Now let me count the number of atoms of A and B to see that the stoichiometry is actually maintained. So these 8 gold atoms contribute 1/8 to this unit cell, that makes it 1, plus these 2 halves give me 1. So there are 2 gold atoms in this structure. These 4 copper atoms are shared between 2 unit cells, that means that gives me 2. So there are 2 gold atoms and 2 copper atoms in this unit cell. That means actually the unit cell formula is Cu2 Au2, which can be written in least we pull out the common factor as Cu Au. So I can see that the stoichiometry is maintained when I am drawing my structure like this. And since there are 4 atoms in this unit cell, 2 of copper, 2 of gold, I can describe this in terms of a notation known as the Pearson symbol, though a little advanced for the stage, but still it is not very difficult to understand. That is, this is a tetragonal structure which shows this T. The P here tells me it is a primitive structure, that means it is no longer a face centered cubic structure, it is very clear, and there are 4 atoms in the unit cell. So this is a tetragonal primitive structure which has 4 atoms in the unit cell. Now let me consider another kind of an ordered alloy, which is also based on my original FCC kind of lattice. So now we of course have to notice in this structure, this is a lattice point, but these are not lattice points. This is, for instance, not a lattice point. This is not a lattice point. This is a primitive structure. This is not a face centered cube. This is a primitive tetragonal structure and not a face centered cubic structure. So this has to be absolutely clear, exactly the same way like we saw that this is simple cubic and not body centered cubic. So similarly, this is not a face centered cubic structure, but actually is a primitive tetragonal crystal. Now similarly, but the way to understand this would be very nice if I can start with the FCC kind of lattice and then try to locate in terms of the FCC lattice where my copper and gold are located. So similarly, I will do the same thing, and this again to emphasize this is a primitive structure. Now the formula is Cu3Au, and let me try to locate my atoms within the unit cell. The gold atoms are all located within the corners or the corners of the unit cell. The copper is located at all the face centers. So again, this is if this is a lattice point, this is not a lattice point, and this is obvious looking at the environment of the atoms. For instance, this has, for instance, another gold atom at its right at a distance of A. Now if I look at this point, it does not have a gold atom to its right at A. So obviously the environment here is different from the environment here, and as I said, we have defined that lattice is such that an array of points is that all points have identical environments. So that environment criteria is not met, therefore if this is a lattice point, this cannot be a lattice point. So the other atoms will have to go part of the motif. Okay. Now the second thing, after putting starting with an original FCC lattice and creating this primitive crystal, I have to note is the stoichiometry. So I have 8 gold atoms making a total of 1 contribution to this unit cell in terms of gold. Okay. Now if I look at the blue copper atoms, which are being colored blue for better visibility, now I can see that there are 6 faces and each one of them is shared half between 2 unit cells. Therefore 6 by 2 is 3, therefore I have 3 copper atoms, which tells me my stoichiometry for the unit cell is Cu3Au. So this is a space filling model of the same, and in this space filling model I can have shown these gold atoms transparent, so that you can see that these inner copper atoms actually form an regular octahedron. So, they are formed in the form of a regular octahedron. So, this blue atoms form an octahedron in the unit cell. Now, what is the crystal structure? This crystal structure is cubic and it is not lost in its three folds. As you can see, these body diagonals, all of them have a three-fold axis, and in fact it has got the highest symmetry for a cubic, which is it's a primitive. It's got 4 by m, 3 bar, 2 by m kind of symmetry, and in the structural Bereshe notation, this is called an L12 symbol. It has been given, this ordered structure has got an L12 symbol, and since it's a cubic crystal, all I need is a single lattice parameter to describe the crystal structure, and the lattice parameter for CuAu is 3.75 angstroms. The Pearson symbol, as I told you, is something easy to understand. The C stands for cubic because this is a cubic crystal. This is a primitive crystal and not a face centered, so I have put a P, and there are 4 atoms in this, or atoms or ions in this unit cell, 3 of them being copper and 1 being gold. There are analogous structures to this U3Au. They happen to be Ni3Al, which is also a technologically important compound, and TiPt3. So, my second structure is Cu3Au, which I understand in terms of the original FCC lattice. So, there are 2 nice structures which I can understand starting from an original FCC lattice, of course modifying it appropriately to fit in different kind of atoms, and accompanied with the kind of atoms I put, there will be distortions to the unit cell obviously, and that is what is being taken care of here.